The main reason that determinants are being taught in your linear algebra course is the fact that they are needed for the computation of eigenvalues of a matrix. However, determinants can be used in many other ways as well. In this video you're going to see how determinants can be used to solve a system of n linear equations in n variables if the solution is unique. More to the point, you're going to learn that for such systems each individual entry of the solution vector is equal to a quotient of two determinants. This technique is called Cramer's rule, named after the Swiss mathematician Gabriel Cramer, who lived from 1704 until 1752. Consider a system A times x is equal to b for some n by n matrix A and vector b in Rn. That is, a system of n linear equations in n variables. You know that the system has a unique solution if and only if the determinant of A is unequal to 0. And that in that case, the solution is equal to the inverse of A times b. The formula x is equal to the inverse of A times b is a closed formula for the solution x. Sometimes one is not interested in the entire solution x, but only in one or two of its entries. So it would be nice if we would have closed formulas for the individual entries, x1 up to xn as well. Let's see what happens in the case of a system A times x is equal to b, where A is a 2 by 2 matrix. So consider A is equal to ABCD and B is equal to PQ. Assume that the determinant of A is unequal to 0, which implies that A is invertible. The inverse of A is given by 1 over AD minus BC times the matrix D minus B minus CA. So the solution x of the system is equal to the expression shown here, which is equal to 1 over AD minus BC times the vector dp minus bq minus cp plus aq. So we find the following formulas for x1 and x2. x1 is equal to dp minus bq divided by ad minus bc, and x2 is equal to minus cp plus aq divided by ad minus bc. Can you already see that each of these formulas is actually the quotient of two determinants? In both formulas, the denominator is equal to the determinant of A. But what about the numerators? Consider the matrix A1b, which is obtained by replacing the first column of A by the right-hand side B. Now have a look again at the formula for x1. The numerator of x1 is equal to the determinant of A1b. Hence, x1 is equal to the determinant of A1b divided by the determinant of A. Similarly, let A2b denote the matrix which is obtained by replacing the second column of A by the vector b, and have another look at the formula for x2. Its numerator is equal to the determinant of A2b, so x2 is equal to the determinant of A2b divided by the determinant of A. The formulas for x1 and x2 given above are an example of the formulas that follow from Cramer's rule for any system of n equations in n variables with a unique solution. Before giving the general result, I'd like to show you an example of a problem which is easily solved by using Cramer's rule. Consider the system A times x is equal to b, where A is equal to the matrix S, 3, minus 2, S plus 5 with parameter S, and B is equal to the vector for 2. Suppose you need to know the answer to the following question. For which values of S does the system have a solution x with x1 equal to 0? To solve this problem, you could, of course, go through the usual motions of row reduction, but in this case the matrix A contains a parameter S, and this makes the method of row reduction somewhat elaborate. Instead, let's try the formula for x1 from Cramer's rule. x1 is equal to the determinant of a1b divided by the determinant of a. With the matrix A and vector B of our example, we find that x1 is equal to the determinant of the matrix 4, 3, 2, s plus 5 divided by the determinant of the matrix S, 3, minus 2, s plus 5, which is equal to 4s plus 14 divided by s plus 2 times s plus 3. And from this we can conclude that the system has a solution with x1 equal to 0 if and only if s is equal to minus 7 over 2. Note that for this value of s the solution is in fact unique because the determinant of a is unequal to 0. Now let's conclude this video with the description of Cramer's rule for the general case. Let A be an invertible n by n matrix. Then, for each vector b in Rn, the system A times x is equal to b has a unique solution x. Now, Cramer's rule states that xi is equal to the determinant of aib divided by the determinant of A, where aib is defined as the matrix which is obtained from the matrix A by replacing the ith column of A by the vector b. A proof of this formula for xi can be found in your book. Cramer's rule is used for theoretical purposes quite often, but it is also useful in lots of practical computational situations. I hope you enjoyed watching this video. In class you will learn some other applications of determinants. See you then.